For thousands of years, every civilization has looked up at the night sky and asked the same question: what is really out there? Each new telescope has pushed that question a little farther, revealing a universe larger, stranger, and more beautiful than anyone expected. Yet few scientific instruments have transformed astronomy as dramatically as the James Webb Space Telescope. When Webb began sending back its first observations, scientists anticipated sharper images and more detailed measurements. What they received instead was a flood of discoveries that challenged long-held assumptions about how the universe evolved. The telescope didn't overturn the laws of physics, but it revealed that nature is often far more efficient and surprising than our theories predicted. One of Webb's greatest strengths is its ability to observe infrared light. This allows it to peer through enormous clouds of cosmic dust that block ordinary visible light, exposing regions where stars and planets are actively forming. Entire stellar nurseries that once appeared dark and empty suddenly became vibrant landscapes filled with newborn stars, glowing gas, and intricate structures shaped by gravity and radiation. As researchers explored these observations, another mystery emerged. Looking farther into space also means looking farther back in time, because light from distant galaxies has traveled for billions of years before reaching Earth. Webb's deep field surveys uncovered galaxies that already appeared surprisingly massive and well organized when the universe was only a small fraction of its current age. Some of these ancient galaxies seemed brighter and more mature than many cosmological models had predicted. Their existence prompted astronomers to revisit simulations of early galaxy formation. Rather than proving existing theories wrong, these observations encouraged scientists to refine their understanding of how quickly stars can form and how rapidly galaxies may assemble under certain conditions. Among the telescope's most remarkable achievements was the direct imaging of the giant exoplanet HIP 65426b. Capturing a picture of a planet orbiting another star is extraordinarily difficult because the overwhelming brightness of the parent star normally hides the much fainter world beside it. Webb's advanced instruments made this observation possible, providing valuable information about the planet's atmosphere and temperature. HIP 65426b is an enormous gas giant several times more massive than Jupiter and orbits its young star at an unusually large distance. Its characteristics continue to challenge astronomers studying planetary formation because such massive worlds are difficult to explain using traditional models alone. Researchers are now investigating several possibilities, including rapid formation through gravitational instability or migration from another location within the system. Another breathtaking phenomenon recorded by Webb involves gravitational lensing. When an extremely massive galaxy lies directly between Earth and a much more distant galaxy, gravity bends the background light, sometimes creating spectacular arcs or even complete rings known as Einstein rings. These nearly perfect circles are among the most beautiful demonstrations of Einstein's theory of general relativity. Although rare, they provide astronomers with powerful natural magnifying glasses that allow them to study galaxies far beyond the reach of ordinary observations. Every new lens offers another opportunity to measure the distribution of matter, including the invisible dark matter that dominates much of the universe's mass. Dark matter itself remains one of modern astronomy's greatest unsolved mysteries. It cannot be observed directly because it neither emits nor reflects light, yet its gravitational influence shapes galaxies and galaxy clusters throughout the cosmos. Webb has contributed valuable observations by helping astronomers map how light bends around massive structures, revealing where dark matter is likely concentrated. Some regions display gravitational effects that are more complex than expected. These observations do not necessarily indicate unknown objects or artificial structures, but they do highlight how much remains to be learned about the invisible components of our universe. Every new measurement improves computer models and helps researchers test competing explanations. Perhaps the most surprising discoveries involve the earliest generations of galaxies. Webb has identified systems that existed only a few 100 million years after the Big Bang. Their brightness, size, and chemical composition continue to fuel lively scientific debate about how quickly galaxies formed during the universe's infancy. Instead of signaling the collapse of modern cosmology, these discoveries represent exactly how science progresses. New evidence forces scientists to ask better questions, improve existing models, and design new observations capable of testing fresh ideas. Every unexpected result becomes another step toward a deeper understanding of the cosmos. As Webb continues scanning distant regions of space, astronomers expect many more surprises. Some mysteries will eventually find straightforward explanations. Others may reshape parts of our understanding of cosmic evolution. Either outcome represents scientific progress because every observation adds another piece to humanity's largest puzzle. And perhaps that is Webb's greatest achievement. Rather than providing all the answers, it reminds us how many extraordinary questions still remain waiting among the stars. Yet the James Webb Space Telescope is doing far more than photographing distant galaxies. Every observation is helping scientists reconstruct the history of the universe with increasing precision. By combining Webb's infrared data with observations from ground-based observatories and other space telescopes, astronomers are building the most detailed picture of cosmic evolution ever assembled. One of the largest structures Webb has helped investigate is the cosmic web, an immense network of galaxy clusters connected by enormous filaments of gas and dark matter stretching across hundreds of millions of light-years. These filaments form the invisible scaffolding upon which galaxies grow, merge, and evolve over billions of years. Although simulations predicted this vast architecture decades ago, Webb's observations are allowing researchers to examine its details with unprecedented clarity. The remarkable organization of these structures often appears almost geometric. Long chains of galaxies intersect at massive clusters while immense voids separate neighboring regions. At first glance, these patterns can seem almost engineered, yet they naturally emerge through gravity acting over immense stretches of time. Even so, each new observation raises fresh questions about how such large-scale structures developed so efficiently in the early universe. Another area where Webb continues to surprise researchers is the study of supermassive black holes. Many galaxies, including our own Milky Way, contain enormous black holes at their centers. Webb has discovered evidence suggesting that some of these giants were already growing rapidly when the universe was remarkably young. Understanding how these objects accumulated so much mass so quickly has become one of modern astrophysics' most important challenges. The telescope has also transformed the search for potentially habitable worlds. By analyzing the faint starlight passing through distant planetary atmospheres during transits, Webb can identify molecules such as water vapor, carbon dioxide, methane, and other compounds. These measurements provide valuable clues about atmospheric chemistry, planetary climates, and the environments that may exist on worlds orbiting distant stars.